Okay, and so let's go ahead and do a quick check and see if that is the solution. So of course, the first thing we need to do is take the derivative because we are dealing with a differential equation. So we have dxp dt, and that's just equal to, of course, then just c over b. So plugging the original function xp and the derivative of that function dxp dt into our original differential equation, we get a times c over b plus then b times the overall function c over b times t minus ac over b squared is equal to c times t if everything has been done correctly. So clearly we get an a over c times b. Distributing the b on across, we get a plus c times t minus an a over c. And of course, this b will cancel with one of the b's in the denominator of that particular term, giving us a negative ac over b. Clearly, these two cancel, and we get c times t, which of course verifies that this xp, this particular solution, solves the differential equation by giving us back the forcing function when we substitute that expression into the differential equation itself. So we recover the forcing function. Now, when we look at this, though, you might be thinking, well, Professor Dinsmore, that's great. And it is a solution. You just showed us that that's a solution. But there's something a little bit disconcerting conceptually about this whole approach. Because notice what I said up here, and let's change colors here. Notice what I said up here is that the particular solution, or the general form for the particular solution that we choose, that we work with, is dependent solely on the input to the differential equation, which means that I have completely ignored, I've only paid attention going all the way back up here, I've only paid attention to the right-hand side of the equation, and I've completely ignored the left-hand side of the equation. Well, I wouldn't say completely ignored it, but at least for the general form of the solution I have. And that isn't terribly satisfying, because when I look at this first order differential equation, at least when we were dealing with them before, when they were set equal to 0, we were getting some kind of exponential response. And yet here we see nothing in the solution that has anything to do with an exponential response. And this becomes even more interesting, even more disconcerting might be the better way to say it, if we go to a second order LTI ODE, because what can we have there? We can have an oscillatory response, we can have an exponential response, we can have combinations of the two, an exponentially growing oscillatory response, exponentially decaying oscillatory response. And yet, in no way does this particular solution even try to address that. So this is kind of leaving us a little bit wanting. It's like, what's going on here? Is the left-hand side of the differential equation just something to help us find the undetermined coefficients, and there's nothing more there to it? Of course, the answer is no, there's more to it. We're clearly missing something in this solution. So sure, it is, mathematically speaking, it is a solution to the differential equation. It does solve it. but we're clearly missing something. So let's go ahead and see if we can find, and as it turns out, we're missing something not only conceptually, we're also missing something mathematically. So here, let's frame where we're going to go next as, is XP the most general solution? Well, so let's see if there's something more that we can do to work with this particular solution that might also yield valid solutions to this differential equation. And again, I'm going to approach this from a bit of a conceptual perspective. So we started with a times dxp dt plus b times xp is equal to c times t. Now, we already showed that that solution works out, so we have no issues there. But let me ask you, can I go ahead and add 0 to this expression? And clearly the answer is sure, I can add 0 and not change anything. So let's go ahead and frame it then as a statement. So I can add 0 to either side of this expression. So I get, and let's do it to the left-hand side, a times dxp dt plus b times xp plus 0 is equal to c times t. So I haven't changed anything. But remember how we are looking at 0. 0 is a little bit different these days, because what can 0 be? 0 can be the result of substituting in the homogeneous solution into the homogeneous form of the differential equation, right? That's why I told you there's a little bit of a spoiler in here, right? Particular solution solves the non-homogeneous form of the ODE, so clearly that was indicating there are other forms. Sure, the homogeneous form's out there, right? And 0 is, of course, just having a little pen trouble here for some reason, is just the result of subbing in, I'll squeeze in there, the homogeneous solution to the homogeneous form, i.e. equal to 0, not equal to our forcing function, of this differential equation. Let's do an IE. Yeah, we'll go ahead and let me erase this. Give me 1 second. Okay. Give me an IE. IE, we can say that A dxh dt plus B, oops, have to get my X in before I write my H. Bxh is equal to 0. And so I have my 0 up here, I have my 0 down here. So there we go. So then we get an even more, well, I shouldn't say more general, we didn't have a general solution before. Now we can find a general solution. So we can say, but first let me capture, where of course, for this first order LTI differential equation, xh is equal to x naught e to the negative, here I'll just say c prime t that we've seen before. So this is the solution to this. Homogeneous form. And that my E got messed up there a little bit. My apologies. Come on, eraser. The ODE. And there we go. This is beautiful because, of course, what do we now have? In our general solution, so first of all, mathematically, this is much more satisfying because we now have another solution to our differential equation, this more general solution, where we're clearly going to be combining what's going on with the particular solution and the homogeneous solution. And then so mathematically, that's more satisfying because again, what happens when I plug in xp plus xh, and we'll go ahead and I'll make it even more general here in a second. Well, when we plug in xp plus xh, the xp portion of the solution is going to give me this guy right here, which will give me c times t. And when we look at the xh portion of the solution, I'm just going to get 0. And so we have this more general solution associated with the differential equation and that more general, so now going back to our engineering side, and that more general solution captures that the system will have more of a role to play in the system response than just determining the undetermined coefficients. It will actually have its own, the nature of its own response will come through as well. In our case, for this first order ODE, we will also see that exponential part of the response coming through in addition to that general linear trend that will also exist because of the particular solution coming from the forcing function and the method of undetermined coefficients. So let's go ahead and capture that. So the most general solution, which is clearly much more mathematically satisfying and, as we can also see, physically necessary to make sure that we capture what the system is doing. So if we have a first order system, we better have some kind of exponential aspect of the response. We have a second order system, we may have exponential, we may have oscillatory, we may have a combination of the two. And so this homogeneous portion of the response is what allows us to see how the system is impacting the or the nature of the system is impacting the overall response, not just the forcing function. Okay, so therefore, most general solution is a combination of the two. Now here I have to be pretty clear. I'm not saying linear combination of the two. So that is important. We'll get to linear combination here in a second, but it is not the linear combination of the two. So again, I'll bring in linear combination, but until then, we'll just say that the overall solution X is equal to XP plus, and here we can take, of course, the homogeneous solution and multiply it by any arbitrary constant we want, because of course the homogeneous solution is just going to give us 0 when we plug it into plug that basis function into the overall or the initial different homogeneous form of the differential equation. And so we're going to get 0, k times 0 is still going to give me 0. So we can multiply it by any arbitrary constant. And so in our particular case, we can say that this is, or in our specific case, I have to be careful with particular now. In our specific case, clearly for this differential equation, we get c over d times t minus ac over, oh, I'm sorry, that's not a d, that's a b. Misread my notes there. Eraser, go ahead and erase. Okay, c over b, there we go, that looks a bit better. Minus a times c over b squared plus, now, k times x naught e to the negative c prime t. And here I'll give you a little recall that, of course, for us, c prime is equal to b over a, as you might recall for the homogeneous case. And if we wanted to, we, of course, could combine this into another constant. And so that's not a problem. Again, that constant is going to be arbitrary as far as the differential equation is concerned, and we will only determine that once we understand either the boundary conditions, or in this case, since it's t, the initial conditions. So let's go ahead and see if everything works out, and of course, it will. So we already checked the particular solution that came about because of our, what we in the math world would call the non-homogeneous side of the differential equation. In the engineering world, we would call that our input or our forcing function. So we already checked that for the particular solution. Now let's go ahead and do it for this overall solution. And so dx dt for our solution is c over b plus x times k naught times negative c prime e to the negative c prime t, and then substituting all of that in, we get a times c times b plus k x naught times negative c prime e to the negative c prime t. And then we get plus, getting a little long here, plus b times, now again, our original overall solution, c times b times t, or c over b times t, my apologies, minus a times c over b squared plus k x naught e to the negative c prime t, and this needs to be equal to c times t. So you can see how all of this kind of breaks into two halves. So we get a times c over b, distributing this b out, but first over the particular portion of the solution, plus, here I'll just do b times c over b, of course the b's will cancel, times t, minus acb over b squared, and of course the b will cancel with the squared there. And we can see, just as we expected, this is all going to be equal to c times t, allowing us to recover the c times t that we have on the right side of the equation. Now let's make sure that the homogeneous portion of the solution gives us 0, which it should. So what do we have? We have plus a times k times x naught. Now remember, this c prime is a negative b over a, So we have to acknowledge that, times e to the negative, but here in the argument, I'll just call it c prime t. And then down here, what do we have? Down here, we have a b, so that's plus b times k x naught e to the negative c prime t. And this whole thing needs to be equal to c times t. So we already saw that the first part gives us our c times t. Now here, let's go ahead and simplify this particular term. So clearly we get a negative k x naught b times e to the negative c prime t. And we can see that, of course, that's just the negative version of the next term, b k x naught e to the negative c prime t, and sure enough, these guys will cancel, and we're just left with c times t. And that's exactly what we would need, is that this is equal to 0, indicating that we're dealing with the homogeneous solution, or the solution, let's say it that way, the solution for the homogeneous form, or one of the solutions for the homogeneous form of the differential equation. In this case, there's only one basis function for that solution space. So that makes perfect sense. And so there we go. Sure enough, that's an even more general solution, because it gives us a solution to the differential equation, but now we're also bringing in the homogeneous portion of the solution, so that's more satisfying mathematically. And as we can see physically, it's absolutely essential, because the method of undetermined coefficients doesn't try to capture at all the nature of the response of the system that led to the differential equation. It's only trying to capture what's going on with the forcing function, and it doesn't even pay attention to what the system is doing other than how it influences the undetermined coefficients. But it doesn't capture the nature of the response of the system. The homogeneous portion does. And so we can see why the homogeneous portion of the solution is absolutely essential from a physical perspective. So let's go ahead and then capture that the most general solution results from summing, again, what we call the particular solution x sub p, which of course is the solution for the non-homogeneous form of the differential equation. Results from summing particular solution with, as we saw last time, now here we can truly say a linear combination. So notice I can't multiply. This is absolutely crucial. I cannot multiply the particular solution by an arbitrary constant, because remember, it doesn't yield 0, right? The whole reason we made that argument that we ended up with all these arbitrary constants with the homogeneous solution is because the basis functions always yielded 0, and multiplying any constant by 0 still gives me 0. That's not the case for the particular solution. We actually get some general function, or some function from, or generally some function from that particular part of the solution. And multiplying by a constant would mess everything up. An arbitrary constant, I would say, or should say, would mess everything up. But again, when we get back to the homogeneous solutions the basis functions, in other words, associated with the homogeneous solution, we can form a linear combination with those, because of course everything winds up being zero regardless of what constants we choose. So with a linear, so notice I use combination above. Here now we have a sum of the particular solution with a linear combination. Okay, so I'll underline that because we're back to our linear combination of the homogeneous solutions otherwise known as the basis functions for the homogeneous solution set, xhi. And so we can write that mathematically. X is equal to xp plus k1 times xh1 plus k2 times xh2 plus all the way on out to plus kn xhn. Or another way we can say it, xp plus xh, where h is that linear combination, and we can express that linear combination if we choose to in a summation I equals 1 to n of ki x h I. So there we go. That is our most general solution for that non-homogeneous differential equation. It clearly captures through the particular solution the effect of the forcing function, and we've already established that the forcing function is going to mirror, or sorry, the particular solution is going to mirror the form of the forcing function. Linear should go to linear, oscillatory should go to oscillatory, exponential should go to exponential, because again, we would be hard pressed to apply a linear forcing function to a system and have absolutely no linear trend in the response. That would be kind of strange. So clearly the particular solution is going to mirror the forcing function, but we also came to realize that since the particular solution doesn't really capture the nature of what's going on with the system, because it doesn't even, when we were selecting the general form for the particular solution, we didn't even consider the order of the differential equation. We were just looking at the forcing function. We didn't even pay attention to the left-hand side of the equation, just the right-hand side. Clearly, that was a less than satisfying result, because we know that the system is going to influence its output in some way, its response in some way. And that's where the homogeneous solution came into play, allowing us to capture what's actually happening with the natural response of the system. And so we can see that we ended up mathematically with a more general result, and we ended up with a much more satisfying solution for the system response that could capture what was going on with the nature of the system itself. Now, let's go ahead and capture that this is, of course, only valid for linear ordinary differential equations. So this method doesn't work for anything but linear ordinary differential equations. And you can see why, because when we start working with the homogeneous solution, what has to happen? We have to be able to, and this is getting into the idea of linear ODEs. When we sum the different components of the solution, i.e. in our case, the response, when we sum those together, for a linear ODE, when we plug that solution back into the ordinary differential equation itself, what needs to happen, just as we saw in this case? Everything associated with a particular solution component, i.e. maybe the particular solution, all those terms need to come together. We need to be able to group them together in order to get what we find on the right-hand side of the equation. And then for each of the terms associated with the individual basis functions for the homogeneous solutions, we need to be able to group those together as well, because each of those will turn into 0. But isn't that the whole point of this definition of linear? That it doesn't matter whether I add things together initially and operate on them, or I operate on them each individually, I end up in the same spot. And so you can see this idea of linear coming into play here, where the homogeneous portions of the differential equation, once we substitute the solution in, those can all be grouped together. And of course, they'll come out to be 0 because they're equal to 0 for the homogeneous form, and the particular solutions will all group together, giving us the forcing function associated with that particular differential equation. Okay, so hopefully you can start to see this idea of how, or how this idea of linear works so well, because it allows us to actually segregate the terms that come from the basis functions associated with the homogeneous solution and segregate the terms associated with the particular solution. And then we can see exactly how that will, those different groupings of terms will come together to allow us to solve the differential equation. So let's go ahead and briefly go over the general forms for the method of undetermined. Oh, missed my AL. General forms. Wow, I'm missing everything there. General forms for the method of undetermined coefficients. Okay. Oh, and before I go there entirely, also to kind of go back to this idea of the linear discussion. Also, what did we say? Because remember, and this was an important thing that I discussed earlier, that truly non-homogeneous differential equations are not really linear. The homogeneous forms are. The non-homogeneous forms are not. And why is that the case? Because you're probably like, well, Professor Dinsmore, you just said that we can either add them together and add all those solutions together and plug them into the differential equation all at once, after taking the appropriate derivatives, of course. Or I could go ahead and operate on each of those solution components individually in the differential equation, and I need to get valid results. Of course, I'd have to sum the individual ones together in order to get the results to be valid. But the kicker is the homogeneous forms are linear, because what do we also have for the homogeneous forms? We can scale them in any way we want and end up in the same spot, right? That was another part of this idea of being linear, is that you can scale them, which is why we can form linear combinations of the basis functions for the homogeneous form of these linear time invariant differential equations, or actually just linear ODEs. Doesn't even have to be time invariant in that particular case. But we can't do that with the particular solution. We can't multiply the particular solution by any arbitrary function. So you can see, I mentioned earlier that a non-homogeneous case is not exactly non-homogeneous case of even something we would call a linear differential equation isn't actually strictly linear, because of what's going on with the, sorry about that, because of what's specifically going on with the particular solution. We don't have that same scaling property that we have for the homogeneous portion of the solution. So hopefully that gives you a better understanding, because we talked about the sum portion of the different components, summing them together works out fine. That's not a problem. But the scaling portion, that's a problem for the particular solution, making non-homogeneous differential equations technically nonlinear based on the strictest definition of being linear or linearity, whereas the homogeneous portions of the solution don't suffer from that same limitation. So we can see homogeneous is linear. The idea of a homogeneous differential equation satisfies all the requirements for being linear. Non-homogeneous one doesn't quite. Okay, which again brings in this important idea that you can't multiply the particular solution by any arbitrary constant you want. Okay, so with that, let's go ahead and move on to the general forms. And as you will see, the forms generally follow the type of forcing function. So in other words, the general form of the forcing function will be mirrored in the form of that is used for the particular solution. And you will see that in this list. So let's run through it quickly. So if we have our differential equation equal to a constant k, the general form for our particular solution is another constant a. Now, if you want to, you can, of course, if you want to make a little bit more sense of this, for this first term, or this first entry, first row, you can say t to the 0, if you like. And then when we get to the next one, if we have t, or anything multiplying that t, of course, we get at plus b. And here I'll just go to a's and b's that I couldn't because I already used a's, b's, and c's in the initial framing of the differential equation for the example. But here we don't have that limitation. And then t squared, we get a squared plus b times t plus c. And so you can see constant, constant, linear, linear, parabolic, parabolic. So it makes perfect sense. Now understand though that here you can have your other terms associated with a parabola. You can have t, something times t to the first power. This would still hold true because even if you substitute in the at plus b plus your a, let's say a prime t plus b prime, and then you add that to the component coming from the squared, what are you going to get? You're going to get an a times t squared plus b times t plus c. Well, the primes are just going to combine with the unprimes, and they're just going to give us different constants. So it doesn't really matter. We know that all those will kind of come together. And so if you have a parabolic form, regardless of the number of terms in that parabolic form, you're just going to use this anyway. So, but with that said, if terms are absent, you might be tempted to have those terms be absent in your assumed form for the particular solution, and you cannot. You have to keep all of those until you show yourself that that undetermined coefficient is truly 0, in which case, yes, for the particular solution, that term is absent. So that's just something that's important to note. But you have to use all the ingredients until you know for sure that one of those coefficients is 0. Okay, so clearly when we go to different powers of the independent variable, we reflect those same powers of the independent variable in the assumed solution, assumed form of the solution for the method of undetermined coefficients. Same thing happens if we have an exponential input. We assume that we're going to have some form of an exponential output. Notice that the argument is the same though. That is important to see. Now let's go to some oscillatory inputs. And as you would expect, you'd be hard-pressed to have an oscillatory input and suddenly get a linear output. That wouldn't make any sense. And so, of course, that's reflected here that we would expect an oscillatory output. So a cosine omega t plus b times sine omega t. And again, you can see that the arguments just map right on over. It's just the coefficients that are going to be a bit different. And we get cosine omega t. And, of course, this makes perfect sense that these arguments would map straight across, especially when we look at the differential equations, because clearly when we take the derivatives of arguments of this nature, the arguments themselves don't change. And so I better have the same argument on the left-hand side of the equation as I have on the right-hand side, because again, the derivatives for these LTI differential equations or these linear differential equations don't change the argument of what's happening with the argument of these particular trigonometric functions. Now let's go ahead and multiply t times some of these functions. And then you can see pretty quickly what happens to the general form. We get an AT plus B, and all that times e to the st. So if we're multiplying them together in general, you can just go ahead and figure out what each general form of the solution would be, and then you just multiply those general forms together. So that generally holds true. Sine omega t. And then we have AT. So this just kind of captures that you do the same thing down here times cosine omega t plus, now here we can have different coefficients though, c times t plus d times sine omega t. And that same trend follows if we have an exponential function multiplied by a trigonometric function. We, of course, would have an e to the st times a cosine omega t plus b times sine. Oh, I'm sorry, didn't mean to close that parenthesis, because that e to the st can be distributed out across both of these. There we go. Now that's the proper way of closing it. And so you can see that if we have any function of time multiplied by e to the st, we would just take the general form associated with the solution for the undetermined coefficients and just multiply that general form by e to the st. And here we can say the same thing about the trigonometric functions. So g of t times sine omega t is just going to be the assumed form associated with the method of undetermined coefficients multiplied by cosine omega t plus potentially a different function times sine, but it would still be the same assumed form, sine omega t, though the constants could clearly be different. Okay, so we can see how conceptually satisfying that is. We excite the system with one particular type of input, and sure enough, we see that same type of input coming back out on through. And so that is very nice indeed that we would be able to see that. So that gives us an understanding of how to use the method of undetermined coefficients to find the particular solution associated with the differential equation, which is a solution of the differential equation, but we found that it's not the most general solution. And that made sense because, of course, the particular solution wasn't trying to directly capture what was happening with the nature of the response associated with the differential equation itself. And so then we have to bring in the homogeneous solution as well to get the most general solution for that differential equation. And that most general solution captures both what's happening with the forcing function, but also captures what's happening with the underlying nature of the system's response itself. And so that, of course, was conceptually satisfying both mathematically, a more general solution, and was much more satisfying from a physical perspective, because we were seeing what was happening with the forcing function and what was happening with the underlying nature of the system's response. And it was all combined together in one solution. So that really combining those specific solutions together really made for a much more conceptually satisfying result. So with that, let's go ahead. And then, of course, we also saw just now that clearly the forms of the inputs will map, or the forms associated with the particular solution might be better way to start. The forms associated with the particular solution map to the same or mirror the same form as the forcing function itself. And that makes perfect sense as well. So let's go ahead and work a couple examples. So first, let's find, and as usual, we'll just do the system response, because of course we're assuming that this differential equation is capturing some type of system. And of course, since we're dealing with these non-homogeneous differential equations, that system is going to be a forced system. So we're going to have some forcing function applied to that system. And so let's have since we already talked first order, let's go to a second order. So we have d squared x dt squared plus x is equal to 40 e to the negative 3t. And here we'll have 0 initial conditions. So we'll have 0 ICs. So clearly, this is, of course, an LTI because the coefficients are constant and the differential equation is obviously linear. Non-homogeneous. Second order, as I said, ODE. And because we're LTI, again, we have constant coefficients. So let's go ahead and start off with, we could either start with the particular solution or the homogeneous solution. And in this case, let's start with the homogeneous solution. And so when we're looking at the homogeneous solution, one of the first things that we want to look at is the characteristic equation. So for this characteristic equation, when we look at the order of these derivatives and the coefficients associated with those particular forms of the function, we clearly get a 1 times s squared for that second derivative. Well, that can just be s squared. And then we just get the coefficient of x by itself, which is just 1. And of course, we set that equal to 0. Now, going ahead and substituting that into the quadratic formula, we get a 0 for our middle term, plus minus square root of that middle term squared, 0 again squared, minus 4 times the first coefficient and the last coefficient. Well, both of those are 1, so we just get a 4, all that over 2. And so we can see pretty quickly that that's just going to be equal to plus minus, so the magnitude 4 square root of that is just 2, but then we still have a square root of -1 over 2. The 2's cancel, so we're just plus or minus square root of -1. Well, that's obviously just j. So we get plus or minus j. Clearly, we're dealing with complex, in this case, actually purely imaginary roots for our characteristic equation. So we have to go to case 3, and we have to substitute those values of s back into the general solution associated, or the general assumed solution associated with that particular case. We kind of distilled it down, though. We did some work back in the day of talking about case 3, and we distilled it down to the fact that we're going to have an e to the real component associated with the root, but our real component here is just 0, technically, times t. But as we can see, that doesn't really matter. And then we're going to have a c prime times cosine. Now, remember here, what is our omega? So we have j omega. Well, we just have 1 times j, so our omega is equal to 1. So that's just going to be cosine omega t is just going to be cosine t plus c double prime sine omega times t, but again, omega is just 1, so we just get t. And so we can see pretty quickly that this is just going to be 1. And as expected, we're going to, since we have purely imaginary roots, we just have a purely oscillatory response. C prime cosine t plus c double prime times sine t. Now again, remember, this is the homogeneous solution. So we then have dxh dt is equal to, and taking the derivatives of these trigonometric functions is pretty simple, so I'm not going to spend a lot of time on that. And then last but not least, d squared xh dt squared is equal to a negative c prime cosine t plus, sorry, let's do the minus, just get that out front, minus c double prime times sine of t. So let's go ahead and just make sure. So we have negative c prime cosine of t times 1, right? This whole thing is times 1. So this is my second derivative times 1 and sine t. And then we get a plus 1 times x. And remember, this is our x up here. C prime cosine t plus c double prime times sine t. And we're looking at the homogeneous form, so this better be equal to 0. Sure enough, we got the negative version of this. We got the negative version of this. Cancel, 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 cancel. Sure enough, this is equal to 0, and we're good. So we got our homogeneous form. So now let's go ahead and look at the particular solution. And so for this particular solution, we can see up here that we are exciting this system with an exponential form, or an exponential forcing function, specifically exponentially decaying. And so then the general form for 40e to the negative 3t, let's do an arrow actually, because we're talking forms. So here we assume that xp is equal to a to the a times e to the, now remember, that argument has to remain exactly the same, as we already discussed, right? So there we go. We just have some unknown coefficient multiplying exactly the same exponential function. So, of course, we need some derivatives. So we get dxp dt is equal to negative 3a e to the negative 3t. And then last but not least, we have d squared xp over dt squared. And that's equal to, of course, 9a e to the negative 3t. So let's go ahead and substitute on in. And when we substitute in, we get 9a e to the negative 3t plus, because again, everything's multiplied by 1, so we just substitute the functions in. A times e to the negative 3t for xp, and of course, that's equal to 40 e to the negative 3t. And so here we can quickly see that obviously the exponential functions are the same, so then we just go ahead and add the coefficients together. So 9a plus 1a is just going to be 10a. E to the negative 3t is equal to 40 times e to the negative 3t. Technically, we could have just started equating coefficients, but that's okay. In this particular case, we'll just divide through and cancel that on out. And then dividing through by 10, we get 4. And clearly, we get pretty quickly that a is equal to 4 for our method of undetermined coefficients. So then our complete solution sorry, got a little rambunctious there with that underline. So that complete solution then is x is equal to xp plus, now remember, we can multiply our homogeneous solution by any arbitrary constant we want. So we can just say that that is plus C triple prime, though it's kind of meaningless because I already formed a linear combination with how we developed case 3. We've already formed a linear combination, but that's okay. We'll just go ahead and run with K triple prime. It doesn't really hurt, times XH. And so it's just we end up with our usual, as I like to call it, constant nightmare, and we get plus C triple prime times C prime times cosine T plus C double prime times sine T. And so, of course, I don't like dealing with the primes. Again, as I indicated in an earlier lecture, I usually use these primes for just kind of stand-in constants. And then once we get to the final constants we want to deal with, I usually put number subscripts on those. So let's go ahead and do that. So then we just get a C1 times cosine T plus C2 times sine T. Now that last step wasn't absolutely necessary, as you could see in this case. And here, let's just go ahead and capture that C1 is equal to C triple prime times C prime, and C2 is equal to C triple prime times C. Whoa, almost did another triple prime there, C double prime. There we go. Now let's go ahead and find the initial conditions. Now, here is something that I want to note because it can be a little easy to get confused. You might be tempted because, of course, we found the undetermined coefficients while we were working with a particular solution, which is absolutely necessary. So you might think, oh, okay, well, you know, the initial conditions are tied to the homogeneous solution. Let's just go ahead and find the constants when we're working with the homogeneous solution by itself. Understand you cannot do that. You will end up you'll end up with wrong results because remember, the initial conditions must work with the overall solution. So even though we're finding these arbitrary constants associated with the homogeneous solution, the overall solution must yield the initial conditions, not just the homogeneous solution. So we have to use the total solution. So x naught is equal to, so we plug in t equals 0, t equals 0, t equals 0. Obviously, this will be 0. This will be this whole one will be 0. Here, cosine will just be 1. Here, the exponential function will just be 1. And so we end up with 4 times 1 plus C1 times 1 plus C2 times 0. And remember that we have 0 initial conditions, so that whole thing is equal to 0. Well, this guy is 0, so we don't have to worry about that. So we just take the 4 over to the other side, get -4, and we can see, and of course that's equal to C1, so we can just essentially by inspection identify that C1 is equal to -4. Now we have to take the derivative of the overall solution. So in our case, we have a -3 coming on down. Now remember that A, we found that to be 4. So we get -3 times 4 times e to the -3t minus C1 that we just found times sine t when we take the derivative of cosine plus C2 times cosine t when we take the derivative of sine. Now plugging in t equals 0 for the initial value of the derivative, And that's equal to negative 12 times, well, we plug in 0 here for t, we obviously just get a 1, minus, and here we plug in 0, sign's just going to be 0, c1 times 0. And here we plug in 0 for t, cosine just becomes 1, plus c2 times 1. And this whole thing is equal to 0. So now we can see that this is just going to be C2. This obviously is going to be 0. This is just going to be negative 12. Take it over to the other side of the equation. That becomes positive 12, and we get C2 is equal to 12. And so then our final form of the solution that not only solves the differential equation in its most general way and captures the initial conditions. Come on, I don't know why my pen isn't coming up. My apologies. There we go. Cosine t plus 12 times sine t. And there we go. So if you want to double check, you can, of course, plug in t equals 0 for x, take the derivative again, plug in t equals 0 for the derivative, and you will end up with the appropriate initial conditions, i.e. everything comes out to be 0. Additionally, you will also see that if you plug this into the differential equation, that sure enough, we end up getting 40 times e to the negative 3t for the, well, let's say it this way, i.e. recovering the right-hand side of the equation by substituting this solution into the left-hand side of the differential equation. So let's now work another example. But this time, so let's find the system response. Let's deal with a different input. Hey, let's spell things correctly. So let's look at our system response like we usually do, but this time we're going to be given the following. We're going to have d squared x dt squared plus 5 dx dt plus 4x is equal to 5 times cosine. So we're going to have a little bit more going on with this problem. We have all three terms represented. We're going to be dealing now with an oscillatory input, and you can see the general form of the solution assumed for the method of undetermined coefficients is clearly a bit more complicated. And we're going to have some non-zero initial conditions this time. So x naught is going to be equal to 0.9, and the initial value of the derivative is going to be equal to 1.9. And again, just like we had last time, this is pretty clearly an LTI because the coefficients are constant and it's clearly a linear differential equation. Also clearly non-homogeneous because kind of pointless to be working with a homogeneous differential equation for the method of undetermined coefficients. And this is, of course, a second order ODE. So again, we're still going to limit ourselves to first and second order ODEs, and that's perfectly fine. We'll get into higher order ones a little bit later in the term. So just like we did last time, let's go ahead and start with the homogeneous solution. So this is something that you should already be relatively familiar with. Don't know why my eraser's having trouble coming up. Let's go back and do this. My apologies. There we go. That looks like it's doing better. So let's go ahead and look at the homogeneous solution. And so we have to start with the characteristic equation, just like we did before. And in this particular case, we can see that we are going to get an s squared, just like we did last time from that second order derivative, but we're going to now have an s to the first power, a term that has s to the first power. So we get an s squared plus 5 times s plus 4. And of course, for the characteristic equation, we're trying to find the roots, so that's equal to 0. So going ahead and substituting into the quadratic formula, we get s1 comma 2 is equal to -5 for the middle term, plus minus root 25, because we take that 5 and square it, minus 4 times the first coefficient is 1 times the last coefficient is 4. And you can see that I conveniently kind of cooked the numbers up here to make things a little bit easier for us. And this is equal to now -5 plus minus root 25 minus 16. Well, that's 9. And all that over 2. And so then that's equal to -5 plus minus 3. So you can see we're dealing with just purely real roots, distinct real roots. So -5 plus 3, that's -2 divided by 2 is -1. -5 minus 3 is -8 divided by 2, that's -4. Okay. So going back to our case 1 and recognizing that our basis functions associated with case 1 are just, and here we'll leave room for the arbitrary constants, e to the -1t. Here I'll just write that as e to the -t plus our next arbitrary constant. So that's our first basis function, e to the -4t. There we go. And then dropping in our arbitrary constants, we get a c prime and a c double prime. So going ahead and doing a quick check, we get dxh dt is clearly equal to -c prime e to the -t. Actually, we need a negative sign. Minus 4c double prime e to the -4t. And then, of course, we need one more. I'll just do that down here. xh dt squared is equal to, so negative cancels, and we just end back up at c prime e to the -t plus now 16c double prime e to the -4t. And so going ahead and substituting in, we simply get our second derivative straight on in, since it has a unity coefficient, double prime e to the -4t. Then we have 5 times now this guy. Actually, we have negative signs, so let's just include those at the outset. -5c prime e to the -t minus 20c double prime e to the -4t. And then last but not least, we have 4 times x, specifically xh, 4c prime e to the -t plus 4 times c double prime e to the -4t. And again, this is our homogeneous solution, so we need to check and make sure that that's equal to 0. And just as we would expect, remember the whole linear discussion that we had before, just as we would expect, even though we're looking at the sum of these two basis functions, actually a linear combination, so a sum of these two scaled basis functions, we better end up in the same spot as if we operated on them individually with the differential equation. And sure enough, we can do exactly that. We can factor out e to the -4t's, e to the -t's, i.e. we can segregate what's happening with each of those basis functions. And sure enough, we get a c prime So that's that one. Here we have an e to the negative t, so we get negative 5c prime. And then last but not least, we have this one here, there we go, plus 4c prime. E to the negative t, which is our basis function. So of course, all those coefficients are just kind of segregated off on their, or can be segregated off on their own. And then we can do the same thing here. We have, here I'll do these in kind of wavy underlines, and we get, well, we don't need that plus sign. We get a 16c double prime minus 12c prime plus 4c double prime, all that times e to the negative 4t is equal to 0. And so what can we see? 1 plus a 4 is 5, negative 5. This guy is 0. What do we get here? We can see a 16 plus a 4 is 20 minus 20, and that's equal to 0, just as we expected. Didn't matter how we scaled them. We could add the scaled versions of those basis functions together, and sure enough, we end up in exactly the same spot. 0 equals 0. Indicating, of course, that the homogeneous form of the differential equation is truly linear when we are looking at differential equations. Of course, again, not true when we're including the particular solution. Remember, please, please do not scale that particular solution. Let me spell out particular solution this time, since it's kind of a new idea. So please do not scale the particular solution by an arbitrary constant or any other constant other than the coefficients, the undetermined coefficients that you found. That's the only thing you can multiply those functions by. Okay, so here, the general form because once we're non-homogeneous, we are no longer strictly linear, even though we still will call it a linear differential equation, because we're really focusing on the homogeneous aspect of that differential equation rather than the non-homogeneous aspect. Okay, so 5 cosine 3t maps into an assumed form for the particular solution of a times cosine 3t plus b times sine 3t. So then our derivative chain looks like this. Negative 3a times now sine 3t plus 3b times now cosine. Oops, not b. Don't ask me why I wanted to write a b there. Cosine 3t. And then we have d squared xp over dt squared. And that's equal to a negative 9, now a times cosine 3t minus 9 times b times sine 3t. And going ahead and substituting in. And here's where things get a little long, so my apologies in advance. So substituting in, we get a negative 9 for our second derivative, negative 9 times a cosine 3t. But hopefully you're seeing, and this is, again, something that I said before, look at what's happening to the argument of all the coefficient functions and the exponential functions. They don't change, right? As I'm taking these different derivatives, they don't change. And so you can see why, when we're assuming the form associated with the method of undetermined coefficients, the form of the function, the argument of the function is exactly the same as that argument associated with the forcing function. Okay, so hopefully you're seeing it, and now you're seeing why that is the case. It's hopefully coming through pretty clearly now, because of course the derivatives don't change that argument. Okay, so negative 9a times cosine 3t minus 9 times b times sine 3t. Now we have a 5 times our first derivative. So we got 5 times this guy minus 15a times sine 3t plus 15b times cosine 3t plus now 4 times, last but not least, our x sub p. And so that's 4b times sine 3t. Oh, my mistake. I missed the first term. My eyes just skipped a term there. My apologies. 4a times cosine 3t plus 4b times sine 3t, and that's equal to 5 times cosine 3t. So again, we can group. Here I won't say segregate, because when I'm talking segregating, it means that we really have some underlying something going on there, specifically associated with a particular basis function. Understand here that we're not really dealing with basis functions anymore. We're just dealing with sines and cosines with no other underlying interpretation. And so because of that, here we're just going to group our sines and the coefficients associated with our sines and cosines. And I use that just to kind of give you that slightly different understanding of what we're doing with the homogeneous solution, so that you can kind of see how those homogeneous solutions are linear. Or I'm sorry, I should say how homogeneous differential equations are truly linear, because we can separate what's going on with the basis functions. Whereas here, these are just different components associated with the assumed solution, the assumed form of the solution. So I just kind of wanted to make sure you see that difference a little bit. And so I am using slightly different terminology so that it makes it a little bit more, it makes it clear that we're kind of interpreting what's going on with these functions and what's going on behind these functions, with our conceptual understanding of what's going on behind these functions a little bit clearer between what we're doing with the particular solution and the homogeneous solution. So with that said, we got cosine, we got cosine, we got cosine. And so we get a negative 9, negative 9a, and we have a plus 15b, and we have a plus 4a, all that. Wow, that 4 really came out ugly. Let's get rid of that. 4a, and all that times cosine 3t. And now let's go ahead and we'll do wavies for the sines. Wavy, wavy, wavy. There we go. And so we get a minus 9b plus, minus 15a. A little premature with that plus there. Minus 15a. And if I've got a little funky, but not enough to erase, plus 4b, and all that times sine 3t, and that's equal to 5 cosine 3t. So when we combine these together, this becomes a negative 5a plus 15b. When we combine these together, that's going to become a negative 15a minus 5b. And so we can now start equating like components, or in this case, components, my apology, like coefficients. And so we can see that there is no sign over here. So if we wanted to, we could have put on the right-hand side plus 0 times sine t, if you like. doesn't hurt. And then that allows us to really see that this coefficient is going to be equal to 5. This coefficient for sine is going to be equal to 0. So that just allows us to see that pretty quickly. So for me, I went ahead and started with my cosine coefficient. So I had that negative 5a plus 15b is equal to 5 coming from the cosines. So that, of course, means that I can go ahead and, so over here we'll deal with sine, but what I can do over here is divide through by 5. That's a pretty obvious common factor for all of the coefficients, 3b, and that's equal to 1. And then last but not least, here I'll just solve for a. So a is equal to 3b minus 1. So this is from our cosine side. Now from the sine side, let's go ahead and we can say that negative 15a minus 5b is clearly equal to 0. Clearly we have 5 as a common factor there, so we get 3a, here I also factored out, I almost made a mistake myself, I factored out a negative sign too, my apologies. So we get a positive 3a plus b is equal to 0. And so then we can go ahead and sub this in over here for a. And when we do, we get 3 times 3b minus 1. I'm sure there's a more elegant way of solving these simultaneous equations, but let's just do it the brute force way. So I get 9b minus 3 plus b is equal to 0. And so I get 10b is equal to 3, and we get that b is equal to 0.3. So now let's substitute back. Here let's do sub in, and here we'll do sub back. Let's put the s first. Almost spelled it backwards there for you. So let's do a sub back. Come on. For some reason my pen isn't coming up. I think it's probably still stuck on the eraser function. There we go. So sub back. And so when I do that, I get a is equal to 3 times 0.3 minus 1. And clearly this is equal to 0.9 minus 1, which is equal to negative 0.1. So there we go. Got my 2 undetermined coefficients figured out. So that allows me then to write my complete solution. So for that complete solution, I have x is equal to xp plus, and here I'll just hold on to multiplying my homogeneous solution by any arbitrary constant, but I've already kind of formed, I'll admit I've kind of formed the, well, not kind of, I've already formed the linear combination. So of course, that's okay, but that just kind of sticks more with the flow of what we've been discussing, so I'm just going to keep running with it. So we get xp plus c triple prime times c prime e to the negative t plus c double prime e to the negative 4t. And so, of course, that's just equal to xp. Here, I'm just going to stick with xp for a second. I don't know why my eraser's having trouble coming up. Come on, eraser, be good. Plus, and so here we can then just say, so I'll keep it at xp until I get to my C1s and C2s. Where, of course, C1 is equal to C triple prime times C single prime, and C2 is equal to C triple prime times C double prime. And so we can then say, and now I will explicitly substitute in for xp, we can say that we get x is equal to negative 0.1 times cosine 3t plus 0.3 times sine 3t plus c1 e to the negative t plus c2 e to the negative 4t. And there we go. Now again, though, we haven't quite finished this problem, and that's important to recognize because we still have to account for the initial conditions. So ICs, so let's go ahead and work with those. Now, what I like to call x naught, x at time equals 0. That one's relatively straightforward. So I go ahead and just plug in t equals 0 for these different terms. Cosine, of course, just becomes 1. Sine becomes 0. The exponential functions just each become 1. So that's relatively simple. So we get negative 0.1 times 1 plus 0.3 times, and here I'll explicitly write out that 0, plus C1 times 1 plus C2 also times 1. And that, of course, is equal to 0.9. Of course, I chose the initial conditions to kind of make the constants work out nicely. So from this, we can see that we get a negative 0.1. We have a positive 0.9 on the other side. Combine those together, of course, that becomes 1. And so we're just left with C1 plus C2 is equal to 1. Here, I went ahead and just solved for C1 because we're going to end up, obviously, with simultaneous equations just like we have before. And so I get a C1 is equal to 1 minus C2. Okay, now for the initial value of the derivative, well, first I have to find the derivative. So dx dt for our overall solution, that's going to be equal to 0.3, a positive 0.3 times sine 3t, because remember, when we're going from cosine to sine, we get a negative sign, and then we get a 3 from here. So that goes out with the 0.1 and combines together to give me 0.3. Now doing the same thing for the next term, we have that 3 coming out, and derivative of sine just becomes a positive sign, so we don't have that switch in sign. We get obviously a 0.9 times cosine 3t minus from the negative 1 times t e to the, need my C1, my apologies, C1 e to the negative t minus 4, when that comes down, C2 e to the negative 4t. So going ahead and substituting in t equals 0, and let's just walk through it quickly. So sine of 0 is just going to be 0, cosine of 0 is going to be 1, and e to the 0, e to the 0, both of those will just become 1s, and we're left with 0.3 times 0 plus 0.9 times 1 minus C1 times 1. Oh, writing a plus, I don't know why, my apologies. Okay, minus 4 times C2. Oh, and let's, since I have for every other term, let's write down the 1 there. Okay, and this is equal to, of course, 1.9. And again, I kind of chose the initial conditions to make the equations kind of nice, so I get negative C1. So we can clearly see what's going to happen. This is a positive 0.9 over here. We got a positive 1.9 over there. The positive 0.9 will go over, subtract off, we'll get a 1. And so then we get negative C1 minus 4 times C2 is equal to 1. So now let's just go ahead and substitute in. For now C1 and we're substituting it into this equation for C1. So colon, and when we do that, we just simply get a negative 1 minus C1 minus 4 times, oh, sorry, C2, because I'm substituting in for C1. C2, there we go, minus 4 times C2, and that's going to be equal to 1. So clearly we get a negative 1 over here, take it on over to the other side, we're going to get a 2. Here we have a negative 1 times a negative 1, that's going to be a positive 1. Positive 1 minus 4 is going to be negative 3. So we end up with a negative 3 C2 is equal to 2, or C2 is equal to negative 2/3. So now back substituting in for C2, we get that C1 is equal to 1 minus negative 2/3, which is equal to 5/3. And so we now have both C1 and C2. Again, this is C1. Let's just go ahead and capture it over here so that way we can see those right there. And so then we get that X is equal to negative 0.1 times cosine 3t plus 0.3 times sine of 3t plus 5/3 times e to the negative t minus 2/3 times sine, there I said sine, my apologies, e to the negative 4t. And there we go. There's our solution that captures the most general solution for that differential equation, i.e. capturing both the particular solution coming from the forcing function and the homogeneous solution coming from how the system will just respond naturally, with constants found that will give us the appropriate initial conditions. So hopefully you can see all of that coming together. So with that, we will call, well, let's go ahead and sum up. So again, summarizing, what have we found? We found that we have a method now for finding the particular solution. Now understand though, and this is important to note, what happens if we run through the method of undetermined coefficients, assuming some kind of general solution, and then the coefficients come out as functions of the independent variable, in our case t, they come out as functions of t, the method failed. If you did everything right, assuming you did everything right, that means that this method has failed and you need to then go to a different method. Just like I said at the beginning, if we're dealing with these differential equations and we try a method of separation of variables and we can't separate the variables, the method of separation of variables failed. And so then we have to go to a different method. And then we might try this method of undetermined coefficients, and the coefficients come out as being variable or being functions, then we got an issue. And so this method may have failed. And so then we need to go to a different method. So that's all that means. If you come out with something where the coefficients turn out to be functions of something rather than constants, then you can say, okay, the method failed. Now we need to try, either I made a mistake or we need to try something else. But nonetheless, assuming everything, or provided that everything works out and we get coefficients that are constant, you then go ahead and form your particular solution. You find your homogeneous, your most general homogeneous solution, i.e. a linear combination of the basis, the homogeneous basis functions, and you just add the two together. Then, and that is the most general, capturing what's going on with the forcing function, capturing what's going on with the underlying behavior of the system, forcing function coming from the particular solution, underlying nature of the system response coming from the homogeneous solution. And then you go and you solve for your initial conditions or boundary conditions that make everything work. And so we've now captured everything that's going on with the system. Initial conditions, the underlying response, fundamental response associated with the system, as well as the forced response of the system. So hopefully you can now see how all of that's coming together. So with that, I will call this video lecture a wrap.